we can now return to our canonical representation of our sequential circuit, and this time we're going to look at this canonical representation when the circuit is a linear sequential circuit instead. So similar as we have for the sequential circuits that are not linear, we have a set of inputs that we call x1 up to xn, so we have n inputs. We have p outputs that we call u1, u2, and then up to up, and then we have r state variables that we call q1, q2, and up to qr. And these variables are seen as the output from our D elements that we have here. So this is our delay elements that we have in our sequential circuit. And for linear sequential circuit, what we have is that this combinational circuit that we have is a linear combinational circuit. This means that our output variables can be written as a linear function in the input variables and the state variables, and also our next state variables can be written as a linear function in our input variables and our state variables. So we can say that our linear sequential circuit is a sequential circuit with only modulo 2 adders and delay elements. And since we can write our next state functions q plus as a linear function in the current state and the input, it means that we can write our q variables like this. So we have r q variables for the next state. This can be written as a matrix times the current state that we have here, plus another matrix times the input, which we call x1 to xn. This is a column vector for all the inputs. And similarly, we can write the outputs u1 up to up as a column vector, and this equals some matrix times the current state q1 to qr plus another matrix times the input variables x1 to xn. So this is just another way of writing, for example, that q1 here is a linear function that is this first row in our matrix times our column vector with q1 to qr plus this first row of this matrix times our column vector of the inputs. And similar for the other next state variables here, and also the same thing for our output variable. So u1 here is the first row of this matrix times the column vector of the current state plus the first row of this matrix times the column vector of the input. And this we do also for all the other output variables that we have. So from this it follows that a linear circuit can always be described by this column vector here of the next state variables, which equals a matrix that we're going to call A. So we call this matrix here A, plus another matrix B times the input variables. So we're going to call this matrix here B. And then the outputs can be written as a column vector, which equals the matrix C. So this matrix here we're going to call C, plus times the current state, plus another matrix that we're going to call H, times the input variables. And we're going to use these matrices when we're finding the reduced form of a linear sequential circuit.